it's off by like negative 200 degrees.
All right.
Correct. That, which may have been part of Evan's calculation.
Okay, good afternoon. Welcome again to Math and Modeling Methods.
Something else wrong.
And this is lecture number 14. Okay, so far in the second part of the semester we've covered ordinary differential equations, first order ordinary differential equations of the exact kind, of the separable kind, of the almost exact kind. Then we talked about linear versions of these equations and how to solve them with integrating factors. Then we talked about numerical methods to solve or to approximate the solutions to these equations. Then we looked at systems of first order differential equations, and we talked about what could be the mechanical or engineering applications of these systems of equations. And what we're going to cover today for the next couple of weeks is how to deal with second order differential equations, which can actually be a little bit more applicable for us in terms of, as mechanical engineers, we encounter many problems that are governed by second order differential equations, whether they are ordinary or partial, which is what we're going to go next. There are many cases in our field of studies that are governed by these equations, and they can be of the kind that are functions of time, or it can be of the kind that are functions of space. We separate them into either initial value problems or boundary value problems. So let's look at how to deal with second order ODEs. Alright, so in general, we can write, a second order linear constant coefficient homogeneous ODE can be written as A times the second y dt squared plus B dy dt plus C y of t is equal to 0. Okay, and you notice why it has all these characteristics. The second order because the highest derivative in the entire equation is the second derivative. It's linear because we don't see any of the dependent function y square multiplying any of the derivatives, or in the argument of a function, rational or irrational transcendental. We see that it's constant coefficients because anything that is multiplying the derivatives is a constant, so it's just basically a linear combination of derivatives of different orders through constants. And it's homogeneous because there is no independent term. The forcing term or non-homogeneous term is equal to 0. Okay? Now, in order to solve this, this is the most basic form of second order ODE. The most basic form is when we have all these conditions met. An auxiliary problem can be set up to determine a non-trivial solution based on the roots. Okay, and we basically are seeking a non-trivial solution because, as you can tell, this equation being homogeneous, a trivial solution will satisfy. Okay, if we pick y equals 0, that would be good for that equation. A y equals 0 will satisfy that equation. But we're looking for a non-trivial solution, a non-zero solution, because we also have to satisfy boundary conditions. So we need a general kind of solution that we can use later to fit coefficients so that we can satisfy also initial conditions. So if we can calculate the roots based on the coefficients a, b, c, we can calculate the roots of this quadratic equation. And that comes from setting up that auxiliary problem, of which I'm not going to go over the details. So if you can find these roots, then you can express the general solution y of t depends on the nature of M1 and 2. And by nature, I mean whether those roots are real, imaginary, or complex. Okay, so first of all, if M1 and 2 are real and different, they're real and different, that would occur when b squared minus 4ac is greater than 0. When that number in the square root is greater than 0, we know we are going to end up with two real and different equations or roots. Then the solution y of t is simply c1 times e to the m1t plus c2 times e to the m2t. So that general solution, and again we call it general because it is a family of solution. Any value of C1 and C2 will satisfy this equation. Or we can also express this as C1 cosine hyperbolic of M1t plus C2 times the sine hyperbolic of M2t. Wait. C1 cosine hyperbolic, sine cosine. M times D. Alright, let's just forget about this for now. We can express this solution in terms of cosine hyperbolic and sine hyperbolic, but we'll have to modify the roots slightly. So let's just leave it like that for now. That will only be necessary when we're talking about boundary value problems. For the case of initial value problems, let's just use the exponential version of these solution. Obviously, cosine hyperbolic and sine hyperbolic are also exponential functions, but we'll have to modify it slightly to make it satisfy. All right, so if those roots are real, that's the solution. If M1 and 2 are real and repeated, that will happen when b squared minus 4ac is equal to 0. When the argument there on the roots, on the quadratic roots, is equal to 0, we end up with the same root repeated. And then the solution looks like c1 e to the mt plus c2t times e to the mt, such that m is equal to m1, which is equal to m2. And 3, if m1, 2 are complex, and that will happen when b squared minus 4ac is less than 0, then we can express the roots as alpha plus minus I beta. Then y of t will be e to the alpha t times c1 times the cosine of beta t plus c2 times the sine of beta t. Right, so this is all news for us. If you remember from differential equations in undergrad, this is the first version of the second order ODE that we saw. Okay? So, By the way, all these three solutions are exactly the same. Okay, we can actually go from this one to this one to this one and vice versa. If we set the solution from complex to real and use complex to real identities, like the Euler identity, for example, where we can transform an exponential function into a combination of trigonometric and exponential function if the argument m1, or m2 in this case, is a complex number. Okay? So, but we can just differentiate them this way. Now the constants of it, the constant of integration, notice that there are two constants of integration now. Of integration C1 and C2 can be determined by imposing two initial conditions. So we need two initial conditions because we have two constants of integration, not just one. So that means that the initial conditions will be y of 0 is equal to y0, and dy dt at time equals 0 will be equal to some b0, whatever that means. Whatever that value y is, if it's position, then dy dt is velocity. If y is anything else, then dy dt corresponds to the first derivative of time of that field function. IVP, this will correspond to an IVP, or initial value problem. And in the case when the function y is a function of space rather than a function of time, or by imposing two boundary conditions, so we can say the boundary conditions can be, for example, y at x1 is equal to y1 and y at x2 is equal to y2. We can have different kinds of boundary conditions, we'll see that later, but this is an example of two boundary conditions. One on one end, the other one on the other end. These are the two boundaries of the problem. So this is a boundary value problem. Boundary value problem. So this is what separates or distinguishes an initial value problem from a boundary value problem. An initial value problem is a problem that depends on time, and all conditions are set at the initial time. So we need two conditions because we have a second order equation. The zero derivative and the first derivative of the resulting function need to be imposed at time equals 0. If we had a third order differential equation, when we need three conditions, so we need first derivative, second derivative, and the value of the function at time equals 0. Okay, in the case of boundary value problems, the problem is bound by two ends. In this case, it's a 1D problem in X. So we need a condition at X equal X1 and another condition at X equal X2, assuming that X1 and X2 are the bounds of the problem. And by the way, this is just an example of how the boundary conditions can be. As I said, there might be other kinds of boundary conditions, but we'll touch upon that later when we concentrate on boundary value problems. Okay. All right, so that's very easy. Yes, sir. So, if we have a second order linear homogeneous constant coefficient ordinary differential equation, that's it. The solution will not escape those three choices there. An imposition of the boundary conditions or initial conditions is pretty straightforward to find the coefficients C1 and C2. And so that's very simple. So now what if the equation is non-homogeneous? So we'll desimplify the problem. We started from the most basic kind, and now we'll add a desimplification. So basically what happens if you still have a linear second order constant coefficient ODE, but now you have a right hand side function which can be a constant or can be a function of time. How do we deal with this? Now, the problem here is that the solution y of t highly depends on the forcing function r of t. We call it the forcing function or the non-homogeneous function or the independent term. Okay? And moreover, a trivial solution doesn't work anymore. Okay, so there's not even the option of saying y is equal to 0 because y equals 0 will not satisfy that equation if r is different than 0. Okay? So we need options. The standard way of approaching this problem is separating the solution. So the solution y of t may be separated into a homogeneous part and a specific part. That is, we can let y of t be equal to y homogeneous plus y specific. So this solution has two parts. And then we can say such that y homogeneous satisfies. So we can say, we can take the same equation that was given to us and remove the right hand side. So remove the non-homogeneity and solve for y of h. And we know how to solve for that. Okay, we get the roots m1 and m2, find whether they're real, imaginary, or repeated real, complex. So find y of h of t using methodology already described. So we know how to find y of h. The specific solution ys of t will depend on the nature of the forcing function r of t. And let's see how that works. I'll give you some examples. Obviously, this is not a general approach, but it is one that could work for several classes of functions. So if r of t is the following, let ys of t be so if r of t is let's say 1 polynomial of degree n. So that function on the right hand side is a polynomial of degree n. Then ys of t, you'll let it be k0 plus k1t plus all the way to kn times t to the n. So you let it be a general polynomial of that same degree. So i.e., let's say that r of t is equal to 3 times t squared. That is a forcing function on the right hand side. Then you're going to let ys of t be equal to k0 plus k1t plus k2 t squared. That's a general polynomial of degree 2. And then we're going to try to fix those coefficients k0, k1, and k2 later. So 2. What if the exponential with argument lambda? So if the forcing function is an exponential function with an argument lambda, then you let y of s be k0 times e to the lambda t. Same argument. So for instance, if r of t is equal to 4e to the minus 2t, then you let ys of t be equal to k0 times e to the minus 2t. You preserve the argument, minus 2 in this case. All right. So 3. If trigonometric function with argument omega. So let's say that we have sine and cosine. Then you're going to let ys be k0 times the cosine of omega t plus k1 times the sine of omega t. So for example, if r of t is given as, let's say, twice the cosine of 3t, then the function that you are going to choose for y of s of t is going to be k0 times the cosine of 3t. You keep the same argument, plus k1 times the sine of 3t. So you have to use the two trigonometric functions, not just the cosine. Alright, so in the fourth and last case that I'm going to discuss, obviously there's many different choices for the forcing function, but these are the common ones and the problems that we will be confronted. So if we have an exponential trigonometric function lambda omega, so an exponential with exponent omega and a trigonometric function with argument omega, with exponent lambda and a trigonometric function with exponent with argument omega, then basically you select e to the lambda t times k0 cosine of omega t plus k1 sine omega t. For example, let's say that RT is given as 4e to the minus 3t times the sine of 2t. Let's say that that's the forcing function on the right hand side. Then the function that you will choose will be e to the minus 3t times k0 times the cosine of 2t plus k1 times the sine of 2t. Alright? So basically it's a pick and choose type of problem. You look at the forcing function, look at the algebraic nature of that function, and select a specific solution that's similar to it. But then you have all these coefficients, k0 through kn, however many you end up with. Then the coefficients k0 through kn, over number of coefficients you end up with, are found through the method of undetermined coefficients, where ys of t is reintroduced into the ODE you reintroduce the solution that you selected into the ODE A to the given ODE plus B dys of t dt squared plus C ys of t is equal to R of t. And then you compare the left to the right. You introduce y of s, whichever one you pick. There, you solve the left and then compare left to right and equate coefficients. So basically, group similar terms and determine k0 through kn using compatibility. Okay, well, this is a relatively straightforward procedure, which we'll explain on an example right away. So, solve the following IBP. So we're given a differential equation, dy dt minus dy dt, and this is squared, minus 2y of t is equal to 10 sine of t. Alright, so we have that linear, second order linear constant coefficient, non-homogeneous ordinary differential equation. There's the non-homogeneous part. All coefficients are constant. This is definitely linear. And given the initial conditions, so this is the governing equation, and the initial conditions are y of 0 is equal to minus 3, and dy dt at 0 is equal to minus 2. So we're given two initial conditions. We need two initial conditions by definition. Okay, so first step, we let y of t be equal to the y homogeneous plus the y specific. Solve homogeneous problem. First, solve for yh of t such that the second derivative of yh of t dt squared minus the first derivative of yh of t dt minus 2 yh of t is equal to 0. So we make the equation that we were given, we just make it homogeneous. So as you can see, A is equal to 1, B is equal to -1, and C is equal to -2. So the roots M12 will be minus 1 plus minus the square root of -1 squared minus 4 times 1 times -2 divided by twice 1. And as you can see, that leads to real roots because the argument b minus 4ac is positive 9. So this is plus minus 3, this is 1 plus minus 3 over 2. That leads to m1 equals to 2, m2 equals to -1. It doesn't really matter what order we express them in. Those are the two roots of the auxiliary problem. So because they're real, y of h of t is equal to c1 e to the 2t plus c2 e to the minus t. That's the homogeneous equation, and it's general because it has two coefficients that need to be fixed or determined through the initial conditions. But we don't do that yet because this is not the actual solution. This is just the homogeneous part of the solution. We need the non-homogeneous part of the solution, the specific part of the solution. All right. So now let's solve for y specific of t, such that r of t, the non-homogeneous term, is 10 sine of t. So what are we going to pick? Therefore, let ys of t be equal to what? We're going to pick trigonometric combination, k0 cosine of t. We keep the same argument. Omega is equal to 1 plus k1 sine of t. And you will immediately see why we keep the same argument. Alright, so if that's the case, if we select ys to be that, then the derivative of ys with respect to t, can you tell me? That will be minus k0 sine of t plus k1 cosine of t. And the second derivative of ys with respect to t squared, the derivative of these will be minus k0 cosine of t minus k1 sine of t. So, if we plug this back into ODE, such that we have the second ys dt squared minus dys dt minus 2 ys of t is equal to 10 sine of t. So we plug all these together. The second derivative will be minus k0 cosine of t minus k1 sine of t minus the first derivative, which is minus k0 sine of t plus k1 cosine of t minus 2 times ys, which is k0 cosine of t plus k1 sine of t is equal to 10 sine of t. So again, the next step will be to group all the cosines together and all the sines together. So we have minus k0 multiplying a cosine, we have minus k1 multiplying a cosine, and we have minus 2k0 multiplying a cosine. So we have minus k0 minus k1 minus 2k0 multiplying the cosine of t, and then we have minus k1, we have plus k0, and then we have minus 2k1 multiplying the sine of t, and that's equal to 10 sine of t. Furthermore, this is equal to minus 3k0 minus k1 times the cosine of t plus k0 minus 3k1 times the sine of t is equal to 10 sine of t. Alright, so now using compatibility, you group the cosines and the sines. So what multiplies a cosine on the left hand side should be equal to what multiplies a cosine on the left hand side. So minus 3k0 minus k1 should be equal to 0, because nothing multiplies a cosine on the left hand side. So we have two equations. We have minus 3k0 minus k1 is equal to 0, and we have k0 minus 3k1 equals to 10. What multiplies the sine on the left should be equal to what multiplies the sine on the right. So basically solve the system of two equations with two unknowns, and you get k0 equals 1 and k1 equals minus 3. So these two values of k0 and k1 will satisfy these two equations simultaneously. And therefore, ys of t is equal to k0, which is 1, so cosine of t minus 3 sine of t. Because that's what we selected. Y of s is k0 cosine t plus k1 sine t. Are there any questions on this procedure? Alright, so now we have the homogeneous part and the specific part. And what we need to do is put it together into the general solution. Y of t is equal to the y homogeneous of t plus the y specific of t. Therefore, y of t is equal to, what we find for the homogeneous was c1 e to the 2t plus c2 e to the minus t, and the y specific is the cosine of t minus 3 sine of t. There we go. So that solution, or it is a family of solutions, it's many different solutions. Any value C1 and C2 will make up a solution, will satisfy that equation. guaranteed. You can try it, or take my word for it. Alright, so that's why we call that the general solution, because it only satisfies the governing equation. It doesn't satisfy the initial value problem, which is a combination of governing equation and initial condition. We need to find C1 and C2 so that we also satisfy specifically the initial conditions. So determine C1 and C2 using initial conditions. And the initial conditions, remember, y of 0 is equal to minus 3, and dy dt at 0 is equal to minus 2. This is what we were given. If y represents the position of something as a function of time, we're told that the initial position is minus 3 and the initial velocity is minus 2. That's all that it means physically. So we take the full general solution, not just the homogeneous part and not just the specific part, the whole thing, and say, well, if y of t is this, then dy dt is equal to, the derivative of these will be 2c1 e to the 2t minus c2 e to the minus t minus the sine of t minus 3 cosine of t, right? And then we can impose the conditions. We can say y at 0, which is equal to c1 plus c2 plus 1 minus 3 times 0 is equal to minus 3. And dy dt at 0 is equal to 2c1 minus c2 minus 0 minus 3 times 1 is equal to minus 2. So what we have is C1 plus C2 is equal to minus 4, and 2C1 minus C2 is equal to 1. So those are two equations, the two unknowns, C1 and C2. We solve the simultaneous equations and get C1 equals minus 1 and C2 equals minus 3. So that would lead to the particular solution. Being y of t is equal to C1, which is minus 1, e to the 2t, C2, which is minus 3, e to the minus t, plus cosine of t minus 3 sine of t. And that is a particular solution because it's actually the particular solution. Because it is a single function that satisfies both the governing equation and the set of initial conditions. All right. Now we have a general methodology to solve linear constant coefficient second order equations. Okay, they can be homogeneous or non-homogeneous. Any questions so far? No questions? All right. Now, how do we go about solving this numerically? We need a numerical solution approach. Sometimes we might not want to bother with going through this analytical solution, or sometimes that function r of t on the right hand side might not be so friendly. Okay, if it's polynomial, if it's trigonometric exponential, it's okay. But if we're given some irrational function with square roots and things like that, we might not be able to get compatibility between the left and the right by selecting an algebraic form for the specific solution. Okay, so we call this a general methodology. Well, it's general as long as the right-hand side function, the forcing function, is framed within these algebraic forms. But if not, then we're in trouble. So we need a numerical approximation approach. Locally, we've already described or formulated a few methods. The Euler, modified Euler, Hoynes, and Runge-Kutta. All of them are family of the same family of solution approaches, prediction correction approaches. And the implementation of them is straightforward. Now we have a second order equation. What do? Do we go back to the Taylor series and approximate the second derivative and plug it in? And then we can do that. But, you know what we did with the first order equation. We had a first order equation. We took the first derivative. We did a Taylor series approximation of the first derivative. Ended up with Euler's method. Or we ended up with the second order Euler's method by truncating the series later. We can do the same for a second order equation, especially when it's linear and constant coefficient like that. We end up with the scheme. But the easiest approach is to use what we already have. We already have Euler's, we already have Hoynes, we already have Runge-Kutta. How would we take that and implement it to a second order equation if that only applies to first order equations? Any ideas? Can we transform the second order equation to first order equation? Huh? How? You can go fourth order to second order?
I thought you could.
Well, not generally, but you can apply some tricks. And it's not that you would transform an equation that's a higher order to a lower order equation, because that will make every equation in the world solvable. Okay? The point is that you can actually create intermediate variables, right? And make up systems of equations that are of lower order. So you can potentially transform a second order equation into two first order equations that are coupled. Or you can take a third order equation and transform it into three first order equations that are coupled by coming up with intermediate variables. Okay? So that's the trick that we're going to play. For the numerical, well, that was the idea, yes. Transforming into a lower order. For the numerical approximation of second order initial value problems, we may transform the second order ODE and initial conditions into a system of two coupled first order ODEs and initial conditions. Okay, so let's play around with the system we have. For example, given the second y dt minus dy dt minus 2 y of t equals to tan sine of t y of t with initial conditions. So this is the governing equation, and the initial conditions are y of 0 equals minus 3, and dy dt at 0 equals minus 2. So this is what we were given, and we ended up with that exact solution, analytical. So why don't we let dy dt be equal to some v of t. In this case, the nomenclature makes sense because if y is position, then v is velocity. But we can just call it whatever we want. Okay, so we're replacing the first derivative of y, which is unknown. We don't know y, and therefore we don't know dy dt. We're replacing it with v. So that means if we plug into ODE, let's plug it into the ordinary differential equation, we end up with, well, if dy dt is equal to v, then the second derivative of y with respect to t squared will be dv dt, right? So dy dt is equal to v, then the second derivative of y with respect to t squared is equal to dv dt. So we can take this into the differential equation, then this is minus dy dt, there will be minus v, minus 2y, stays as minus 2y, is equal to 10 sine of t. Therefore, the system of ODEs, first order, is, so now we have two simultaneous equations. Let's see, one that says dy dt is equal to v of t, and another one that says dv dt is equal to 2y of t plus v of t plus 10 sine of t. So now we have a system of simultaneous ODEs. We cannot solve for y because we don't know v. We cannot solve for v because we don't know y. They're coupled. Okay? But we can solve for them simultaneously through the methods that we learned, either analytically using the eigenvalue decomposition, or numerically using the implementation of the Euler's and Hoynes method and so on for systems of ODEs. So, basically let y equal to, or y of t equals to y1 of t, and v of t equals to y2 of t. And this is the same nomenclature we used when we looked at systems of ordinary differential equations. So now we have dy dt, that would be y1 prime of t equals to 0 y1 plus 1 y2. y2 prime of t will be equal to 2 y1 of t plus 1 y2 of t plus 10 sine of t. So we can write this or written as y dot of t equals to a of t times y of t plus g of t. This will be y1 of t, y2 of t, got it, is equal to 0, 1, 2, 1, y1 of t, y2 of t, plus 0 times and sine of t. So there's a system of equation that corresponds exactly to the given second order ODE, where y1 represents the solution y that we're looking for, and y2 represents the derivative of that function y that we're looking for. And with initial conditions, y1 of 0, y2 of 0 equals -3, -2. All right? I wrote a MathCAD spreadsheet for this particular example, and it's basically the same MathCAD spreadsheet that we presented last Thursday for the systems of ODEs. It's just basically applied to this particular problem, and then we can compare it. We can compare the solution y1 to this exact solution. All right? I can show you at the end of the class today, but that will be posted on Canvas as well. So let me continue with today's lecture for a few minutes. Let me introduce another concept, and then if I have time at the end of the lecture, I'll show you the MathCAD spreadsheet. All right. So we start with the most basic form of the second order ODE, where we have constant coefficients. It's linear, constant coefficients and non-homogeneous. Solution is pretty straightforward. We eliminated one particular simplification, which was the non-homogeneous part. We made it non-homogeneous, and so we found a way of getting to a solution. Now, what happens if we have a variable coefficient homogeneous linear ODE? Variable coefficient. Homogeneous linear ODEs of second order. We're still talking about second order. So we can write this as the second y dx squared plus px dyx dx plus qx y of x is equal to 0. Now notice that I switched t to x, and I did this for a specific reason, because often you will encounter in engineering problems situations when the problem is governed by a second order ODE with variable coefficients like this. That would happen in boundary value problems rather than in initial value problems. Okay, cases such as in heat transfer, when you have fin problems where y is the temperature of the fin in the direction of the fin, you can use the derivative of that to calculate the amount of heat removed, and so on and so forth, are governed by equations of these types, of these forms. So notice that we change from y of t, which corresponds to an initial value problem, to y of x, which corresponds to a boundary value problem, because most of these problems will arise when solving BVPs. Okay. Well, the problem is that there's not a general methodology that guarantees a solution to these ODEs. Okay? We cannot frame them into a specific class and say, we'll do this, we'll get a solution. Okay? It depends highly on what PX is and what QX is. But There's not a general technique. But because it's a linear equation, we can always say, well, as long as px and qx are singular of some kind, are non-singular, sorry, we are guaranteed a solution. We know that the solution exists. We just don't have a method that will get us there, that will guarantee us to get us there. So in general, we can expect a solution in the form. So we know that we'll get something that looks like C0 times f of x plus C1 times g of x. Okay, we know that we're going to end up with two constants of integration because this is a second order equation. We know that we have two boundary conditions to fix those two constants of integration. Okay, now one specific variable coefficient, second order, linear ODE, known as the Euler-Cauchy equation, has a simple solution approach. It is only in these cases when the equation happens to be of this form: x squared, the second y, the x squared, plus ax, the y, the x of x, plus b, y of x, is equal to 0. Okay, so that's definitely a variable coefficient. Notice that p of x is equal to a divided by x, and q of x is equal to b divided by x squared. Okay, so it's definitely a variable coefficient ODE. It is linear, it's homogeneous, and but it's definitely variable coefficient. Okay? So only in the cases where we have a second degree polynomial, second degree function, not even a polynomial, multiplying the second derivative, a first degree polynomial multiplying the first derivative, and a 0 degree polynomial or constant multiplying y, we can call this an Euler-Cauchy equation, and that Euler-Cauchy equation has a well-known solution approach. In this case, we can try a solution y1 of x is equal to x to the m. We don't know what m is, but we can try that. And if that's the case, the y1 dx is equal to m times x to the m minus 1. And if that's the case, the second derivative of y1 dx squared is equal to m times m minus 1 x to the m minus 2. Here. No. All right. So if we plug this back into ODE, we'll get x squared times the second derivative of y with respect to the x squared, which is this much, m times m minus 1 times x to the m minus 2, plus ax times the first derivative of y, which is m times x to the m minus 1, plus b times the function y of x that we are trying, and that's equal to 0. And as you can see, then x squared times x to the m minus 2 will be x to the m. So here we end up with m times m minus 1 times x to the m plus a m times x to the m plus b x to the m is equal to 0. Then we can take a common factor. And then the only way for these to be a non-trivial solution is if that is 0. So for this product to be 0, either what's in the brackets is 0 or x to the m is 0. But if x to the m is 0, then that will lead to a trivial solution. We don't want a trivial solution. So for a non-trivial solution, then m times m minus 1 plus am plus b must be equal to 0. And that means we can expand this. That will be m squared plus a minus 1 times m plus b is equal to 0. And that will mean that we can find m1 and 2 as the roots of this polynomial. 1 minus a plus minus the square root of a minus 1 squared minus 4 times 1 times b divided by 2. So any of those two values of m will satisfy the equation. So now we have two solutions, y1 corresponding to m1 and y2 corresponding to m2. But now we have the problem of whether this is a real or a complex set of roots. So, to end the class today, so 1, if m1 and 2 are real and different, that means that the argument there in the square root is positive, greater than 0, then y of x is equal to c1 times x to the m1 plus c2 times x to the m2. And there's the two constants of integration, c1 and c2, which can be fixed using the boundary conditions. 2, if m1 and 2 are real and repeated, that means that the argument there on the inside the square root is 0, then y of x is equal to c1 plus c2 times log of x times x to the m. Such that m is equal to m1, which is equal to m2. And 3, if m1 and 2 are complex, meaning that m1 and 2 is equal to alpha plus minus I beta, the solution y of x is equal to x to the alpha times c1 times the cosine of beta log of x plus c2 times the sine of beta log of x. And that's it. And that is the solution to the Cauchy-Euler equation, or the Euler-Cauchy equation. But it's very, very restricted because the equation has to look like this. We have to have an x squared, an x, and a 1 multiplied times the coefficient. And then the equation, the solution ends up being like that. So unfortunately, this solution only applies to the Euler-Cauchy equation. And general variable coefficients second order linear ODEs do not follow this simple solution approach. Okay? So when we get back next week, because there's no classes Thursday, remember it's fall break, we'll look at how do we go about solving them when they're general, and you'll find out that the methodology is not as straightforward as what we've seen so far for every one of the equations that we've laid down. All right? So I'll post that math spreadsheet on Canvas as well as his notes. Remember, it's just basically the same one as last Thursday's, but it's just applied to this problem that we solved today. All right? So, any questions? By the way, I posted assignment number 2. You won't be able to solve most of the problems in assignment number 2. I think it's 8 problems, 6, I can't remember. So you'll be able to solve about half of them right now at this point. So you can use part of the full break to solve those so that it doesn't accumulate for the next 2 weeks. It is due on Tuesday, 2 weeks from now, exactly. All right?
It's not sure. Sometimes A over L. This is has to get A over L.
I was wondering why you were.
Oh, by the way, the homework. I posted the homework scores on Canvas. You can pick up your papers here.